Thank you. The first thing I'd like to mention is I did the CSDMS spring school the 1 year it wasn't ESPN in 2022. And so at that point, I made a grid that I didn't know at the time would not work. And then also my only Python coding was that one where you like put things in a bag and then you take them out of the bag and you make a little game when you first learn Python sometimes. And I had no idea what GitHub was. And so this is just what happened since 2022. All right, so this is the Lake Pontchartrain estuary. So I'm going to take you guys all the way down to the other end of the Mississippi River. The Lake Pontchartrain estuary is in coastal Louisiana, east of the Mississippi River. It's large, shallow, and wide. And kind of pointing to Crystal's talk, it actually was originally named Okatawa, which means wide water by the Tangipahoa tribe, which is something that really drives a lot of the dynamics. And then it's also semi-enclosed. It has 2 small tidal inlets, and then it is brackish, but very low salinity, about 4.5 PSU. It receives fresh water from multiple tributaries, and then it is intermittently connected to the Mississippi River due to a freshwater diversion. So if you're not familiar with a freshwater diversion, there are engineered structures that redirect water from one channel, such as the Mississippi River to Lake Pontchartrain in our case. And this freshwater diversion is called the Bonnie Carey Spillway. The Bonnie Carey Spillway was built after the flood of 1927, and since it has opened about 16 times, and over half of, or just about half of those times have been since 2008. And so one of the reasons this was constructed is to really avoid New Orleans getting flooded the same way it did. So it's one of those things, it has to open. The result, if it doesn't, is catastrophic. But there are some ecological considerations that we do have to consider. So a couple of things with these operational trends. If you look at water level at the spillway, it has increased about 2.6 centimeters a year. So that's about 2 feet since the year 2000. And so this diversion has 3 operational states. The first one is it's actually open, so we call those operational flows. And so if you look at the left on that figure, you can see that that gate is wide open. The second is non-operational leakage, so that's water that comes between the slats. This was built in 1927. It's a very early structure. And then the third one is when it's closed and there's no flow coming through at all. So I do want to show that if you look at the right side, that is where it's leaking through the slats. And so the figure down on the left, you can see the number of days there's been non-operational leakage in red and operational discharge in the blue teal color. And you can see in the past few years, it has increased in the number of days and how frequently we see those discharges. And so one of the things that this means is there's a lot of water that's coming into Lake Pontchartrain. And with that, that means there's a lot of nutrients also coming in, all of the things that the Mississippi River carries. And so one of the things to think about is when we look at the Mississippi River watershed since the 60s to about the 2000s, if you see in dark red, we have a very large increase in the amount of nitrogen coming through. And one of the things with this nitrogen nutrients means that we're seeing more algal blooms where nearly half the world's population in coastal areas is struggling from algal growth, but not just your traditional when you think of ocean coastal, but also the Great Lakes, as you guys know, definitely experiences it quite a bit and was the inspiration for the original proposal. And so one of the things is that harmful algal blooms in Lake Pontchartrain have been correlated to discharge from the Bonnie Carey Spillway. So a couple of things about these algal blooms. You can see this young child swimming in it. They are dangerous. They can cause long-term disease, especially if you have asthma. It also really affects fisheries, which is the heart and soul of Louisiana. And so It's something that when these blooms do occur, there's notices that go out to fisheries as well to let them know what's going on and where to avoid. And so in Lake Pontchartrain, why did the blooms get so bad? And so I showed you guys a couple of things about Lake Pontchartrain, but they have a particular type of bacteria called cyanobacteria. I'm not going to go too much into the bio today. But basically, what they need is they need nutrients. So we have that discharge from the Mississippi River intermittently, which gives them nutrients to grow. And then those nutrients also do settle into the ground, into the sediment. And then when you have hurricanes, which we have a lot in Louisiana, it picks it up so we can get more of those algal blooms again, and as well as cold fronts. There's also a lot of tributaries along the northern shore, which introduces even more nutrients. So those are those rivers I pointed out before. Again, it's large, so that's plenty of surface area for them to grow. It's shallow, meaning the water warms very quickly. And Louisiana, if you've been there, is quite warm already, so they already have the temperature that they need. And then it's also limited flushing and semi-enclosed. So that means that the amount of time that water spends in that system is more than enough for them to grow and multiply. But one of the questions I first asked when I was learning all about Lake Pontchartrain and the algal blooms is if it's primarily in the literature caused by the spillway, why is it happening in years when the spillway isn't open? And so there were a couple of papers that just said, hey, maybe it's the tributaries or there might be leakage from the diversion. And so that's where a lot of this work really found its legs, was trying to see, okay, well, how are these causing it? It's much less studied. So these are the two research questions that I focused on throughout my dissertation. And one of them is, again, how does non-operational leakage and tributary inflows impact water transport and cyanohabs? And then the next one, which is where you'll see more about gauge predict, is can we predict potential diversion influence cyanohab hotspots days to weeks in advance? And the reason we want to do that earlier is because if we need to warn fisheries, we can start to identify, hey, these regions might start to be impacted, or even sometimes we're given a couple days notice that the diversion is going to open, and organizing a field campaign that quickly is pretty tough. And then also there's some work I know that's going on in University of Alabama and in Florida, where they're starting to think of mitigation strategies when blooms actually do occur. And so in order to solve this problem, or try to at least wrap my head around it, I created a framework to quantify how the upstream conditions throughout the Mississippi River Basin drive downstream water transport and impact water quality in Lake Pontchartrain. And so I'm going to go through kind of two main parts. With this, I'm going to show some modeling. I'm not going to go into a lot of the nitty gritty. I will give resources to where all of that is, or please feel free to ask me at any point during the conference. And so the first one is going to be a hydrodynamic model built with Delft 3D. And that's going to look at tributary discharge and the role the diversion has for water transport throughout the system. And then the second is, or why do we want to understand this? Again, it's zones with longer water transport timescales, create conditions for cyanohabs. And then the second is for understanding these upstream conditions for prediction. I'm going to show what Gauge Predict was, and it is a basin-wide machine learning model that predicts daily downstream discharge days to weeks in advance. So first, I'm going to show just quickly the Lake Pontchartrain model. These are available on HydroShare. This particular one, this is the paper for it. It is validated and calibrated for water depth and velocity. Coming soon and will be online very shortly. It works, it's calibrated, I just have to make everything make sense to somebody other than me. But we have finally figured out composite temperature and salinity. And so with this, if anyone knows my advisor, Matt Hite, I made him a GitHub that will hopefully get used called Hydrology Town. And so it has all the Delft 3D file creation, model setup and definitions, validation, further calibration if needed, and analysis notebooks. And so, yeah, I'll start to show you a little bit of what found it. So The first thing I looked at was the relationship between Mississippi River discharge and the Lake Pontchartrain tributaries. If you look, the tributaries are up on that northern shore, and then the diversion is down at the southern shore, so they're pretty far spread apart. And so when I looked at kind of the statistical trends, it was a weak positive correlation, which basically states that these systems primarily interact independently of each other. And so for the model, I can explain this further if anyone has any questions later, but basically instead of modeling one single diversion event, I took all of the diversion events and kind of did a composite one so we could look at general trends. And then I did a similar kind of process with tributary discharge where I looked at the low, median, and high based on the 90th, 50th, and 10th percentiles of discharge. And so that gave us 6 scenarios to understand what's happening when the diversion is open and when the diversion is closed under those tributary discharge conditions. And so in order to quantify water transport, I used exposure time. I'm excited to be at this conference because I can go more into the methods than I usually get to. But basically exposure time is a cumulative time water spends in a region of interest, including reentries. So think residence time, but it can leave and come back. And this is really useful for coastal environments where you have tidal flux. And so I did this using Dorado. And Dorado is in the CSDMS repository. It utilizes a weighted random walk routing scheme. Particle movement is driven by water level and velocity. And so as part of this, a new model component was added. And so there's a notebook on how to use that and how to integrate Delft 3D into Dorado. And so for Lake Pontchartrain, first I seeded 20,000 particles throughout the system. And so in order to quantify the relationship, we use these curves. So it's a cumulative density curve, which we call exposure time distribution. And so basically, if you look at the x-axis, you see the time in days, and then the distribution is saying 100% or 100% of particles have left the system when it's at the top. So to make this make a little more sense, when we hit 50% of particles, you see that line right there. We're saying that at about 17 days right there, 50% of particles have exited the system. And so I stole kind of the sedimentologies where you guys do like E50, E90 and all that. I stole that kind of idea for understanding that E50 of 50% of particles leaving the system, 75% of particles leaving the system, and then 90% of particles leaving the system. And so one thing that you'll find is interesting as me is that when the diversion is closed, it has 0 effect. I reran the model twice. I was very shocked by that. It does make sense. A lot of people said when you're creating the Lake Pontchartrain model, you don't need to include the tributaries. This proved that that was very wrong. And actually, it was a local who said, hey, you should include that, and it ended up being the entire paper. So it made a lot of sense to just listen to somebody. And so a couple of things to see. Yep, there's no variation really. If you zoom it in, there's like very tiny fluctuations, but nothing really measurable. And then when the diversion is open, exposure time can be 2 times longer under low tributary discharge conditions. And so we're seeing that, okay, there is a modulation of water transport due to the interaction of tributary conditions and diversion flows. And so this gives us a 1 number answer for the entire system, but I wanted to understand how is this happening spatially, because 1 number doesn't really help the fisheries. It doesn't help us figure out where to sample. So what I did is I first looked at what we called spatial system-wide exposure time, and that's the time it takes for 1 particle to exit the system. And so first we seeded Lake Pontchartrain with particles. And then in dark red, you can see that's where it was tracked throughout the system. And then when it goes to that lighter red, it stops counting how long it's in there. And then when it turns dark red again, it counts it again. And so then the domain was partitioned into gridded cells. And then in each of those gridded cells, I again did that curve and then had it just export those 3 values. And so this was an add-on where I got a lot of help from Kyle, Jay, and Mark for making it all work together and not breaking Dorado on them. Um, and so one of the main things we found, I'm just going to focus on when it's closed and then the E90. Just the reason why we're looking at E90 is traces of, even if you have 10% of that original water, that can hold enough nutrients to spark those blooms. So again, when we even look spatially, we see that there's no very minimal variation in spatial exposure time when the diversion is closed. But when it's open, you do see that that northern shore really starts to increase in how long exposure time lasts. And so this got me thinking, though, we're seeing where water starts and then it leaves, but what about circulation? What about trapping? And so when you have eddies, or in the case of Lake Pontchartrain, we actually get something that they'll even classify as a gyre just because it's so large. And so in order to separate this, I did something called what we're calling localized exposure time. And then if a particle starts in that purple box and leaves the box and then comes back in, we just see how long it remained in that box. And so this really shows us areas where stagnant water and nutrient-rich water can easily warm and create blooms. And so we can see that, again, for the closed diversion, not much really changed. It changed a little bit more than other ones, but again, it's still really hard to tell. But when we look at those open diversion scenarios, you see that you get, again, that center gyre I was saying that exists in Lake Pontchartrain. You see it in the, where it's starting to trap and circulate. And so we're seeing that low discharge can produce these new zones of longer exposure time, which are more likely to cause blooms. And then also adds to the spatial extent as well as the length of time. And so then we could conclude that background tributary conditions modulate diversion flows and exposure time in the system. And then the last one for this 2D that we wanted to look at was, what about the particles originating in the system? So one of the things with Lake Pontchartrain is you always have kind of these background nutrients sitting there, but then you get even more coming in again through the spillway. And so when we look at those conditions, we do get that similar pattern where you get larger zones. But if we look at the high discharge, one thing that was very interesting to us is that it causes a short circuiting, where then you get this zone closer to that smaller little lake you can see on the left, that just nothing is from the spillway gets into that area. So you're kind of getting a trapping of water from, again, that little lake, and then water that's already in the system. So I know somebody who's taking the model after me is going to start looking at what's coming out of that lake and where it's going. And so because of this, can we predict potential hotspots of increased exposure time? So then this is where Gauge Predict comes into play. So what I did was I took basin-wide discharge data. I used it to predict downstream water levels 1 to 30 days in advance. And then using those water levels, I then used a modified Weir equation to then quantify the discharge. And again, because early forecasting provides time to organize water sampling and hazard mitigation. And so this model, again, it's on GitHub. It's called Gauge Predict. Feel free to check it out. And so in order to create this data set, machine learning models, they're stats. It's informed with data and data that you really need to know what's going into it. And so first, I took all of the sites from the Mississippi River Basin and then looked at sites that had greater than 95% data availability, and then split it into a training and test set. And so the training data was input into the model. And so I used a CNN LSTM, which a convolutional neural network. The main thing you need to understand with that is it understands these like short-term events, like rapid rises and falls and relationships between gauges. And then the long-term gives you the context of those events and can also help learn from those background conditions. And so then through that, we then took the water levels that it predicted for that time frame. But one of the things and one of the biggest complaints about machine learning models is we don't know how it's quote unquote thinking. And Joe uses a good term for his models, does it think like a geomorphologist? So did our model think like a hydrologist? And so we use something called a SHAP analysis. And so basically what this does is when you're looking at it, you see in dark blue what points the model considered least important in its decision making. And then in yellow, it's the ones that it considered most important. So this was done for two reasons. The first, again, we wanted to know how the model learned. And so you can see it behaved kind of how we expected, where it's getting the most information between 1 and 5 days, really close to the source. And then as you move into that 10 and 30-day mark, you start to see it hit the Ohio River. You see it start to hit around here and up in Montana. And then the second reason we use this is because we can identify out of those 1,900 sites which ones are most important. So then we can make it lightweight and run faster, so you can just run it on any machine. So it took the sites down to maximum 135 for kind of the largest example I could think of. And then it reduced the computational time from 54 minutes to 5. If you're using your GPU, you can get it much faster than that even. And so these are the results we got for our test data for the Bonnie Carey Spillways water level. And you can see that prediction was very accurate between 1 and 5 days with high accuracy at 10 days. And then timing and appearance of peaks were captured around 30 days, but they weren't quite as accurate, which is what we would expect. Is pretty hard to predict 30 days out, but we can start to get a general idea. So how does water level impact the diversion? And so basically all I'm going to explain with this equation, this is the Weir equation. Water level is entered into the equation as a time series. And then we have this fractional component. When it's not open, it's the fraction of the entire system where water can leak through. And then when it is open, we have the number of gates open that the Army Corps reports. We can also kind of look at this again too and suggest about how many should be open to keep their numbers the way they want them. And then also including the closed channels where water can also leak through. And so I'm just going to show the ones for sorry, I am showing both, sorry about that. So in 2020, we had an opening that year. And so we wanted to see if we could accurately forecast that. When forecasting in this particular way, you do have to take some of the human decisions in the sense that they have a particular threshold. So you have to enter that in, and then they opened a particular number of gates. So it is partially informed by the number of gates that they chose and calculated through their own systems. And so we can see that it closely matched between 1 and 15 days. But then you can see that area or that error band increases a lot as time moves further. And so for non-operational leakage, it actually was a lot more accurate for that, probably because there's less human decisions involved, and it's just what's coming through the structure. The Army Corps used to report these numbers, so I had it for this year when they did report leakage. They don't report it anymore because papers have come out saying that the leakage is harmful, so it's not as easy to find, which is part of the reason we wanted to figure out how to do it. And so you can see that it matched similarly well with differences between 40 meters cubed per second between 1 and 10 days, which in the grand scheme of how much discharge comes through those systems, that is pretty good. And so we wanted to apply this again spatially and see. So the results I'm going to show you are very preliminary in the sense that I did not put nearly enough particles in the system because it was a proof of concept and takes a while to run Dorado on my machine because I haven't set the GPU up yet for that. But so you can see, again, we're looking at those two separate years. So the green dotted line is leakage and the blue line is discharge. And so the leakage year, we did see that exposure time was actually a lot less than the year it opened. And so we looked at total river flow locally in the system, and there were some local rainfall events, as well as a Category 4 hurricane that went directly through Lake Pontchartrain. And so we can kind of understand that that's why the system flushed the way it did. And so for that year, for the operational, when we look at what happened spatially, we see that that northern shore again really had water just kind of sitting in the system for system-wide. And then when we were starting now to integrate the satellite biological maps. And here you can see we're starting to see some relationships between where we're getting these algal bloom hotspots. One of the things with the southern shore is this, if you're familiar with New Orleans, this model does not include pumps, but I have an engineering undergrad who wants to do that this summer. So we get to have pumps going through New Orleans now in the model. So continuing work is to kind of create this as an automatic pipeline so it's better for prediction. Calibrating with NASA's cyano index, and then the eventually a phytoplankton adaptation model. And so that's part of why we're getting the temperature and salinity. But I told you guys that there was this really cool tool that was made. So I'm gonna quickly go through what this is. And so basically what I built is Gauge Predict. So I just explained how it worked. But one of the things of what made this a research tool and not that could be for anybody and not just for my project was that I kind of saw early stages of what it could do. And so I was like, oh, if I could predict one gauge for my purpose, well, I could do this for a bunch of other things. And so one of the things that's nice about making a research tool like this is you actually do less because you don't want to hard code specific things early on. So you get those quick little wins. Later, you end up having to do more that you don't realize at the beginning, but you do hard code a lot less. And then what this tool can do is I set it up so it doesn't have to be USGS data. It can also be CSVs. I've put in NOAA data. It works for mathematically if you're in a tidal system. So lately, as funding has been dropping in some areas, Louisiana has been impacted by that. Some gauges are no longer being monitored. And so I don't have the results for it now because we're still working it through. But one of the gauges is pretty important for some of the oyster research and shrimp research that they have is just completely offline. And so we're able now to hindcast and try to see if we can at least give a little bit of information there. And then, so when I tested to see if we could do this, predict not just a day in advance, but about an hour in advance, it was accurate as well there too. And so some gauges, USGS will actually give you that hindcast when the station goes out, but not many of them. So we were able to test it with the Mississippi River where they do give you that type of information. And so incoming updates, partially due to reviewer requests, is that there's now an option to not use the CNN LSTM, but you can use the components, you can switch the order, or you can use persistence comparisons. And then also updating for USGS water data because their data retrieval is no longer being used. So when you're using those large swaths of data, it's going to be a little bit more difficult. But if anybody's interested in contributing, it is not just hydrological data. I set it up that you can use any biological parameter from USGS or any CSV file that you have. So if you're interested, find me on GitHub or you can talk to me here. And then, I missed that one. Yeah, it was the thank you slide. There we go. All right, I do want to thank Lynn. I've sent you so many emails this summer and coming here. And so just thank you for everything. And then my hosts this summer were Albert, Arena, and Greg. And then my advisor, Matt, and then Joe Martin from CU. And then for GitHub assistance from Mark, Kyle, and Jay, who are pretty involved in this community. So if you have any questions on any of the models, I did put my CV on there only because that's where I do have a list of every single link. And it just seemed like the easiest way to do it. So yeah, if you have any questions, let me know.
Thank you, Katie. We have time for one question. Jeff.
So what he asked was if he had about 10 sites and he had a logger of some sort that you want to measure about 10 times, you said, would that work? That you need a good amount of data if you want it to be pretty accurate, but that is system dependent. So I found that with one, if we were including wind and a couple closer parameters, we were able to predict it pretty accurately, but it was all very local. So the larger out you move depends, but that amount of data that you need is kind of situationally dependent. Does that answer your question?